There are a few groups who are asking me for discussion on nonlinear effects in optical fiber, since we deal nonlinear effect in our system all the time. So I thought to create this session. So thank you all for joining this session. So in this talk, basically, I'm going to discuss about what are the nonlinear effects, how it affect our system, how we try to mitigate them, and how other effect can come into the future system as well. So there in this talk, I'm not going to discuss too much detail in the mathematics, little bit about the physics, little bit some equations, not much. But if it's too much, then you can tell me in between. Uh, so let's just start. Uh, so why we talk about nonlinearity? Nonlinear effect in optical fiber is basically why, because of we have a DWDM optical transmission system. All of our system is DWDM. And the main aim of this transmission system is to transmit the bits from transmitter to receiver successfully. And how we do it in DWDM system is we try to modulate this data in a DWDM channel and multiplex it together, transmit it through the series of amplifier and optical fiber through various number of spans till it reaches to the receiver side. At the receiver side, what we do, we demultiplex them. We try to demodulate the data back to the original bit format. And in order to
Abhishek,
this, yeah,
sorry to disturb. Can you press
hmm,
Control L so that laser pointer will show?
uh, sure, yeah. So, in order this to happen very correctly, or in order to faithfully recover the original data bits, what we need is high OSNR. So, what do you mean by high OSNR? OSNR is defined as a signal power divided by noise power. Means if there is a high OSNR, means you have a high signal power and low noise power. So, if you have a high OSNR, you can basically have a recovery of your data because the noise effect is very low. And every transceiver, basically at the TSP receiver, there is a minimum amount of OSNR needed, which is defined by various vendor that how much minimum threshold required in order to faithfully recover these data bits. So all we need is to increase the OSNR of the system, and we are able to successfully transmit the data. So to increase the OSNR, what we can do, we can just increase the signal power, which looks very straightforward, and that will increase the OSNR. So we increase the signal power, and then what we expect is to increase in OSNR. But actually, it doesn't happen. What happens actually when we increase the signal power, the OSNR slowly degrade, and then it reaches to certain optimum value, and then it start to decrease. And this curve, which is also known as a bell curve, so this happened because of the non-linearity in the fiber. The non-linear X start to X at the higher power, and because of that, OSNR start to degrade. So as you see, the linear effect, which occurs only at the lower power, this consists of the noise coming from the AC noise of the amplifier. At the higher power, the nonlinear effect in the fiber start to take place, and so which is more dominant than the linear one, and so the OSNR start to decrease. We see this in terms of GOSNR in our system, and we have this metric as well where you can see this effect. Now, if you see the spectrum, uh, the black one is the transmitted spectrum, and if you see the linear range where the power is low, so only the AC noise occurs. The AC noise can be modeled as a white Gaussian noise, means this noise present at almost every frequency. So because of the AC noise and because the nonlinear noise is very low, the signal spectrum doesn't change almost in the linear regime. While in the nonlinear regime, what happened that the nonlinear noise comes place, and the nonlinear noise has the shape of the signal itself. Means when the signal is present, then only the nonlinear noise will present, and when the nonlinear noise is dominant than the linear noise at higher power, this takes place, and you can see this green spectrum. And in presence of nonlinear noise, because of nonlinearity, the tails of the signal changes. Whereas in the linear domain, the tail of the signal doesn't change, as you can see in the spectrum. So even we try to increase the OSNR by increase the signal power, we are never able to get the high OSNR because of the fiber nonlinearity. So what we do, we try to bias our transmitter or transceivers at the optimum power. Means we try to transmit as much as possible maximum power we can send to get the maximum OSNR, or at least we try to do that. Whether we're successful or not, that's another picture. So to understand more about the how this nonlinear effect happen in the fiber, let's dig down a little bit to the physics of the fiber nonlinearity. So we can define the fiber nonlinearity in two parts. One is called elastic effect and another one is called inelastic effect. So in elastic effect, the optical energy is conserved, and it can be further divided into three parts: self-phase modulation, cross-phase modulation, and four-way mixing. We are going to see how this actually affect our system. And then there is inelastic effect, where the optical energy is not conserved. Mainly they are SRS and SBS, Raman effect and Brillouin effect. The Raman effect, it does affect us a lot, especially in our C plus L band system. And the Brillouin effect, we are still studying. It might occur more in the longer transmission distance, especially when we talk about 4,000 kilometer and so on. So there, this effect will be very, very high. So let's start with the elastic effect first. So why elastic effect happen? To understand this, we need to understand what happens if we transmit a laser or the optics modulated light through the fiber. Now, if you understand, the laser is basically a series of photons, and photon at the higher power has high momentum. And this high momentum photon interact with the molecules and electron of a fiber. So what it does is basically try to change the position of molecules and electrons. And because of this redistribution of the molecules and electrons in the lattice of fiber, there is a temporal shift in the refractive index. So at the lower power, when the power is very low, this momentum is very low. So nonlinear. So the refractive index of the fiber is very constant. It doesn't change. But at the higher power, because of the fiber radius is very small, so even at very low power, the intensity is very high, and this nonlinear effect will come into the picture, which changes the refractive index of the fiber depending upon the intensity of the signal itself. So what I meant to say, that when you transmit a laser through the fiber, it changes the refractive index of the fiber itself at higher power, relatively higher power. And since there is a nonlinear change in refractive index in the fiber, it directly translates to the phase change. So a signal in the laser, when it passes in the fiber, when it passes through a length L, is the phase of the signal changes according to this equation. And that depends upon the effective refractive index. And since there is a nonlinear part to play off, so phase change in the signal also depend upon the nonlinear part of the fiber. This means the phase change of the signal depend upon the power or intensity of the signal itself, which is temporary, as long as when there is a signal is present. And this phase change manifests itself into three effects, which called SPM, XPN, and four-way mixing, WWDM. Now, you can see this nonlinearity or nonlinear refractive index in various terms in the literature, either as a nonlinear refractive index or third order nonlinearity, also defined as chi3, which depend upon nonlinear refractive index. Or in more general, you can see in the data sheet the value which is called gamma, which is called nonlinearity coefficient, which again depend upon this nonlinear refractive index. And typical value of gamma is 1.25 per watt per kilometer for a standard single mode fiber G652. And some of the fiber is higher, some of the fiber is lower. We'll see that in later slides. So let's start again with self-phase modulation and try to understand how the self-phase modulation occurs because of this nonlinear refractive index changes. So let's see if we transmit a signal pulse. This is what we do in our system. We transmit signal pulse, and so in a spectrum, it looks like something like this, but in the time domain, it looks like this. When we transmit this kind of pulses, there are two different pulses here. So when we can see that the optical power of the signal itself changing with the time because of we transmit the pulses. And so it changes the phase of the signal because of the nonlinear refractive index in this very similar fashion. So basically the phase of the signal is getting changed or getting modulated because of its own variation in the power. So it's called self-phase modulation. So it's creating a modulation in its phase because of its own power variation. And this self-phase modulation or the phase changing with time causes something called chirping. Chirping is frequencies change in signal with the time. So if you differentiate this, you can get the frequency change, and the frequency change happen because of the self-phase modulation. So this chirping, which is frequency change, it happen in two ways, something called red shift and then something in blue shift. Means it changes the carrier frequency either in lower side or in higher side or on both. So because of this chirping, what happened to the transmitted spectrum? The transmitted spectrum was actually this one, but after passing through certain length of the fiber, it gets broadened or get distorted. And this broadened and distorted causes the problem at the receiver end. So the immediate effect of self-phase modulation is broadening of the pulse. Now, the self-phase modulation happened because of the channel changes its phase because of its on power. Okay, so what happened if there is more than one channel? So in the DWDM system, we transmit multiple channel. So in the multiple channel system, the phase of a signal doesn't change just only because of its own power variation, but it can change because of the power variation in other channel. So basically, different channel can start cross-talking because of the cross-phase modulation. So in the cross-phase modulation, any channel phase changes because of power variation in other channel in the system. So that's called cross-phase modulation. So if you have a multiple channel transmission, as in DWDM system, there is both self-phase modulation and cross-phase modulation both occur. Both of them affect only the phase of system, means it doesn't contribute anything to the power transfer, just the phase transfer. So because of this phase, and you remember the signal information lies in phase, so it can easily cause the crosstalk. So this phase change can be modeled as the phase noise. So basically, self-phase modulation and cross-phase modulation acts as a phase noise. These systems are more effective at higher baud rate system because phase variation with the time and intensity variation with the time is higher for higher baud rate system. So SPM and XPM is more effective when you have very high baud rate systems or for high coherent modulation format for QPSK to 16-com or 8-com. These effects are very effective. The interesting thing about the SPM and XPM that with dispersion they cancel out each other, because the dispersion again can also cause chirping. Means dispersion also changes the carrier frequency in positive or negative region, means increasing or decreasing the carrier frequency, but it happen in an opposite way than the SPM and XPM. So dispersion and this self and cross phase modulation acts opposite to each other. So basically dispersion reduces this effect in the system. And so dispersion is good for a system with higher modulation format or higher baud rate system. The next one is four-wave mixing. So the four-wave mixing happened because of the third order nonlinearity. What does it mean is the third order nonlinearity involves three channels or three waves, and which result in generation of the fourth channel or fourth frequency. Since four waves are involved, three original and one generated wave, so it's called four-wave mixing. In four-wave mixing, any two channel or even one channel can act as a pump, and this pump channel, which has usually higher intensity, interact with a relatively lower intensity of the channel and create a new channel or new frequency, as you can see in this diagram. And the frequency of the newly generated channel or frequency is defined by this equation. So in DWDM system where there are many channels, any three channel can basically crosstalk or can create a crosstalk and cause a fourth frequency generation. In this entire process, both energy and momentum must be conserved. Energy is always conserved, as you can see from this equation. Energy conservation means the initial pump frequency added together must be equal to the third frequency plus new frequency generation. That's always happened. But the phase matching, which is coming out because of the momentum conservation, this may or may not be present. If there is a perfect phase matching, means the phase of the two pumps is equal to the phase of the third channel plus the newly generated phase. If this condition is met, this means four-wave mixing is very efficient and the very high power of the four-wave mixing product, which means the fourth frequency will be very high power if this condition is matched. So the interesting thing about the four-wave mixing is that any channel, doesn't matter. These two can also act as a pump and work with this third to generate this, and so on. So any two channel or any even single channel can act as a pump, work with another frequency or another channel and generate the fourth wave. Now, since let's say in 100 gigahertz channel spacing of DWDM system, there is 48 channel. This means this 48 channel, you can select any three channel, and this three channel can generate the fourth channel. So there are various ways you can generate the many number of four-way mixing product out of three channel from 48 channel. So for end of DWDM channel, actually you can generate various number of four-way mixing product. For example, for n, it is n square n minus 1 by 2, which is very huge number of four-way mixing product can be possible. So for example, n equal to 5 may result in 50 four-way mixing product. Of course, not all of the four-way mixing product are efficient. Some of them are not efficient because of the phase matching conditions are not met, or they are deviated from the perfect phase matching. But some of them could be very effective, and this means the high power can be generated because of the four-way mixing. So let's take an example of the n equal to 3, means there is only 3 channel participating. So if there is only 3 channel participating, so these are the 9 four-way mixing product possible. What happens if these 3 channels are at equal channel spacing? There is an interesting effect happen if they are in equal channel spacing. These are the result from the one of the experiment. As you can see, if the channel number we select is 30, 31, and 32, the generated 9 four-way mixing product are these. And you can see the generated four-way mixing product lie, 3 of them lie on the original channel transmission. This means the four-way mixing product might lie in the original channel spectrum if the channel spacing are equal, and that's one of the disadvantage of four-way mixing. So if you keep the equal channel spacing in DWDM system, the four-way mixing product falls on the same channel, which leads to crosstalk, and which means there is a bit error, or you can think as a noise. So one of the things we must consider is not keeping the equal channel spacing while we plan for a DWDM transmission system. So how to avoid the unequal channel, how to create unequal channel spacing or avoid the equal channel spacing. So for example, n equal to 3, we can select three channels which are not equal. So 30, 31, and 33. So here between F1 and F2, there is 100 gigahertz channel spacing. Between F2 and F3, there is 200 gigahertz channel spacing. So channel spacings are not equal. And so if you fit to the previous equation, what we get is this green. So these 3 are original channel, and these greens are the four-way mixing product. As you see, this four-way mixing product doesn't lie in the original transmission channels. So they lie out of the band of the actual signal, and so easily can be either filtered out by ROADM or filter, or even it's not filtered out, it's still, if it is present, still it acts as a noise, not causing any sort of crosstalk. So for n equal to 3, this is the case. For n equal to 4 and so on, you can select various way how you can select the 4 channel or 5 channel and so on without causing the equal channel spacing. Unfortunately, for 100 gigahertz channel spacing, you can have only 8 channel which are unequally spaced to each other. If you have more than 8 channel, some of the channel might fall in the similar channel spacing, and so the generated four-way mixing product always cause crosstalk. For 50 gigahertz generation bandwidth, it's a 12 number of channel having unequal channel spacing. So how the four-way mixing affect the DWDM transmission system? First is loss of channel power. Channel power is transferred from either one channel to other channel, or creating a new product. It's create a new frequency, new generation, new frequency, which acts as a noise. And then if we have a large number of DWDM channel, which is usually in our case, it can create huge number of four-way mixing product. It's vary like almost exponentially. So you can see n equal to 8, it became 224. N equal to 5, it was 50. N equal to 3, it was 9. So it's increases very huge if n is increases. Of course, all of them are not very efficient, but some of them could be very efficient and cause problems. One of the biggest challenge is to have a equal channel in unequal channel spacing. If you have equal channel spacing, this might cause crosstalk, and all of them result in decrease in OSNR. So how to avoid the four-way mixing? So one of the way to avoid the four-way mixing is to create a large channel spacing. But what we usually do. Recently also, Yoram, if you remember, we have some issue with the 4,000 kilometer fiber. So we try to increase the channel spacing. And increasing the channel spacing basically decrease the phase matching condition. So means your phase matching cannot be matched, and because of that, four-way mixing efficiency will be low. So effect of non-linearity can be reduced. So usually we go to this part, like we try to increase the channel spacing if it is possible to reduce the effect of four-way mixing. Another way to go is if it is possible to create unequal channel spacing. That also can reduce the effect of four-way mixing. Still, it creates the four-way mixing product, but it doesn't cause crosstalk. The another effect which is more important is again the fiber dispersion. The large fiber dispersion because the dispersion changes the phase of the signal, so which leads to a poor phase matching condition. Means the phase matching condition doesn't meet if you have a high fiber dispersion. So the fiber dispersion is also good for four-way mixing because it creates the low four-way mixing efficiency. So for example, if you use a G653 fiber, which is a zero dispersion shifted fiber, which has zero dispersion almost at 1550, which has very low dispersion in C-band region, so it might have very high four-way mixing efficiency because dispersion is very small. And so if you design very long-range system or with a very high baud rate or QPSK or more than that, we should avoid G653 for longer distances. So if you summarize, yeah.
Sorry, I have a question on the previous slide.
Yeah.
So basically, was if customer, or let's say we wanted to utilize entire spacing of C band and L band, in that case there should be a trade-off, right? Because if I use the first two methods, I cannot utilize entire channels because I have to give a larger spacing or an equal channel spacing. Is that true?
That's true. Unfortunately, like when we design a system, we always look for the worst condition, and worst condition is when everything is occupied, right? So
Yeah.
in that case, yes, we can't avoid it. That's true. So then in that case, we need to monitor the nonlinearity, how the nonlinear effect, like affect the entire system, and based on that, we design the how much power we can transmit and so far. And that's I'm going to discuss in the next slide. But you are right. This is not always possible, but whenever it's possible, we can do. At least in some testing, it's possible, so we can do. Right.
Just one comment. Network planner should take it in account. So whatever network planner approve will work. Should work.
Yeah, that's fine, Amir. But what I'm trying to say is when we say we wanted to control the non-linearity by using the techniques, okay, either it can be the channel spacing or Goldman method or whatever it is. But it's not that with that when customer want to skews out of everything, right? Whatever is possible in the band. Whether now we are talking L band, earlier it was only C band. So what in nutshell I'm trying to say that FWM cannot be avoided fully. In the network, in the actual network.
Yeah, it cannot be fully avoided when you have an entire spectrum is filled in the worst case. No, so yeah, you're right. It cannot be. Recently, we had a POC and we are facing some problems. So what we did the first part, increasing the channel spacing, and it worked, if I remember correctly. So some part it does work, but at the end we can't avoid. Yeah, but we have some other function which we can try, which I'm going to discuss next, which is
Thank
not
you,
this
Abhishek.
one. Yeah.
Abhishek, I have one question. Like
Yeah.
in a live scenario, how we can know like there is causing four-way mixing? Like what things you really check to see that there is four-way mixing?
Okay. So one thing is you can't separate the four-way mixing with other effect. Like for example, four-way mixing happen at least when there is at least two channel. One of them is act as a pump, another is like idler. So we can't actually see exactly unless you see the spectrum. You don't see. So for example, if you have to see this spectrum, that then you can see there is a four-way mixing product. Otherwise, there is a SPM, XPM, and four-way mixing all together happening together. We can't separate from each other. So we can't actually see that whether four-way mixing is happening alone or not. It's not possible. Yeah, but what is possible is to monitor the pump, monitor the transmission power, and we can see that how the OSNR is degrading when you have multiple channel. And that's the test we do in our lab as well.
Okay, so
Abhishek?
what you really see, like you said, how the OSNR is degrading. Okay, so you
Yeah.
see some immediate OSNR degrade at some point,
So
or,
I
or,
will
or
come
what is
to
the
that.
behavior?
So you have if you remember this graph in the beginning I discussed. This is the actual behavior. You can see the something like this to happen. This means there is a nonlinear effect is playing off. It's no longer linear. So this is the one thing you can see. But I'm going to discuss in the next slide that how we monitor there is this nonlinear effect present in the system or not. So that's the next point. I will show you here where the optical energy is not conserved, and there is two effects: Raman effect and the Brillouin effect. So Raman effect, which is interesting because we deal with this within our C plus L band system. So how the Raman effect happen? Because we transmit this channel when we transmit large number of channel, basically, it interact with the molecular vibration of the fiber, and it transfers some of the energy to those molecular vibration, as in terms of phonon. Basically, you are going to increase the temperature of fiber through the transmitting the higher power. And since you are transferring some energy, so its frequency is changing. So there is a transfer of power from higher frequency to the lower frequency, and that happened because of the Raman effect. It's a very famous effect which happen everywhere, in gases, in molecules, in solid. So it's also happened in the fiber. So because of the Raman effect, what happened, if you are transmitting the equal power, for example, in C band, because of the Raman effect, the higher frequency or lower wavelength transmits some of the power to the higher wavelength or lower frequency. And because of that, there is a tilt in channel power, and tilt in channel power means tilt in OSNR as well. So this happened because of the Raman effect. And what we do for that, we use amplifier to compensate this tilt and the loss. Because of Raman also effect causes loss. So the middle channel suffers with the loss, and we define it as a SRS loss. Another channel, we define SRS tilt, from which is last minus first channel loss. And so this loss and tilt happen in the system because of the Raman effect, and an amplifier compensate both tilt and loss. So this so far good, because of these values are not very high. If there is only C band system, the SRS loss is almost 0. On tilt there is some value of tilt, but which can be easily compensated by amplifier. But what happens when there is a L band? So when we add L band, this tilt, as you can see, is increases both in C band and it's also present in L band. So we must compensate the tilt when there is L band channel added. Other than that, if you have certain add and drop in L band, or you are upgrading from C to L band, this SRS loss and SRS tilt will change, and we need to compensate it. Also depend upon where the channel lies, what is the channel power, and etc. So any add and drop is going to change the tilt, and you need to, the amplifier need to know how much to compensate. So this we did with our C plus L band system. We try to model the SRS loss and tilt, which we try to model it as a function of power per channel population and distribution, means where the channel occurs, like where in C band actually is a channel present, and what effect it can cause in SRS loss and tilt, and also on the different fiber parameters. And we did a lot of simulations and also experiments. So with the various of simulations, we find out this equation, which is SRS loss and tilt equation, which basically depend upon various parameter. For example, C total power in C and L band, as well as depend upon the distribution of channels. So this factor U and eta basically says that depend upon the number of channel. I'm not giving the equation here, but the U factor is uniformity distribution, means it takes care of where the channel are present actually in the system. So we define the C and L band uniformity, which depend upon U factor as such. If you have symmetric channel, means either symmetric or fully populated, the value is 1. If it is blue, then it's greater than 1 and less than 1 for the red channel. So this take care of the channel population and distribution in the equation, and then we can give this equation to the amplifier to compensate accordingly, and then we can compensate. We also verified with terms of lab experiment and the simulation equation, and we found very perfect match. Not perfect, but good enough match for us. And then in our system, we compensated SRS tilt and SRS loss, pre and post compensated. Most of you know about it. It takes around 16 milliseconds to compensate. So whenever we have L band drop or add, there is increase in power, and how you bring it back to original. We apply those equation, and those equation acts, and it get back to the original power within 60 milliseconds. Not original, very near to original, and then original because of the ONCP cycle. It happened after a few seconds and come back to the original power. So this is how the Raman effect work in C plus L DWDM system, and this is how we try to compensate it. We already have this in India, as you know about it. We didn't do the field testing, but still it's with our customer. Okay, so next one is stimulated Brillouin effect. This effect is relatively, it's very old effect, but the people have started to investigate this in the optical networking industry very recently, and there was a lot of talk about it. So here what happened, the laser, the optical wave, it not interact with just with the molecules, but it also basically what happened when you're transmitting the pump or you're transmitting the laser, it create acoustic wave it creates a stress wave. Basically, you're transmitting the high power, which is on and off for a long time, frequently. So it creates acoustic wave. A variation in the radiation pressure causes the acoustic wave, and so some of the energy goes to the acoustic wave, Now, acoustic wave usually lies around 50 megahertz. So some of the energy transfer happen between a channel within 50 megahertz channel space, 15 megahertz frequency separation. And because of that, the Brillouin effect happen. Brillouin effect result in the channel reflection in the backward direction. Means channel is propagating in certain direction. The Brillouin scattered wave occur in the backward direction. So it looks very similar to Rayleigh backscattering. The Rayleigh backscattering happen at the lower power. It's always happened, by the way, because of the molecules and everything. There is a scattering center because of impurities, and it reflects back the power. That's the Rayleigh effect. But when you increase the power because of the radiation pressure noise or variation, the Brillouin effect takes place, and so after certain power, the Brillouin effect is very high. As you can see, the power for the SBS threshold doesn't require too much. It's very low, around 0 or 1 dB. Still, SBS can happen. So that's why it's gain attention these days, and the reason to gain attention is this. The gain coefficient for SBS for single mode fiber is 100 times higher than Raman SRS. This means even at the lower threshold power, the SBS can happen. But in order to see the SBS, either we need long transmission distance because it's happened very slowly, very low power with the distance. So it requires very large distance to see effectively the SBS. But once SBS happen, what it can cause loss in signal power. It can cause phase noise, very similar to decrease in OSNR. It can cause depolarization of signal, which is also an issue at the receiver, at the DSP, because of the SBS create the SBS create the birefringes, and because of that, this depolarization happen. It can cause modulation instability because this effect happen within the channel. It doesn't happen inter-channel, it happen intra-channel. So modulation can change. That's another thing happen. And then transmission transceiver destabilization can happen because of the reflected power. Another effect which I didn't mention here is when you have large number of SBS happen, this SBS power, this SBS spectrum actually interact with the scattering center and create a forward scattered wave again. Instead of backward scattered, it also create a forward scattered wave, and that again adds additional noise and can cause crosstalk as well. So these effects can happen, and by the way, these effects inversely depend upon the area effective of the fiber. So for the single mode fiber where area is very small, these effects are very higher. So we need to consider this effect as well. So there are certain talks about it, and in these days, and they try to find out the spectrum because of the SBS. They transmitted a continuous wave laser, and they found this acoustic mode around 50 megahertz spacing. They also measure the GOFs or SBS efficiency, and it decreases with the effective area. So they also tried to do experiment, and they found a similar thing. Further, they did 8-com transmission for 160 kilometer SSFM, and still they found this. You can see these modes, which is at the 50 megahertz exactly. So these modes are present within the with the modulation channel as well. So this means it could be problematic for us as well. So how it affect the modulated channel? So this is the channel. For example, this is, let's say, 33 gigawatt channel, and you are transmitting. It's passing through the fiber. So what happened because of the fiber, because of the Brillouin effect, there is a frequency shifted replica, which is 50 megahertz shifted entirely, happened, which transmit in the backward direction. It could transmit in the forward direction as well after certain power level. And since it transmit along the distance, so after going through certain distance, it's going to grow up, and because of this creating new spectra, the spectrum of the channel itself is shifting. It's also changing because it's happening at 50 megahertz. So at certain length, it's called 100,000 kilometers, there's a spectrum preservation length, means the spectrum of the channel will not change because of the Brillouin effect. But after 2,000 kilometers, that's called coherence restriction length, the spectrum of the channel itself can change and maybe can cause certain penalty or noise. The problem is the dispersion. Dispersion here actually enhances the Gauss effect. So in the nonlinear effect, the elastic nonlinear effect, dispersion is opposing the other effect, so it's good for us. But here dispersion is worse for us, and since we are not using DCF in the fiber in our transmission system, this means Gauss can increase, the Brillouin effect can increase more, and so on. So there were some talk, and they started to talk about creating a penalty, suitable penalty, considering the Boolean effect as a noise source again, and they model this as this term. And they found that the Gauss or Boolean effect can cause up to 0.6 dB penalty. And besides this is also we have seen in we didn't see the Gauss effect yet, but we have seen some difference in simulation and lab, which is also very similar around 0.6 dB. So this can give us some idea as well that maybe the Gauss or Boolean effect can present in our system, especially when we talk about 4,000 kilometer now in those area, and when you talk about at least more than 2,000 kilometer, this effect definitely can present, and especially in the certain baud rate system. So we are also planning. Yeah.
Yeah, in that case, let's say if link is less than 1,000 kilometers, still this penalty will be applicable?
No, it's not applicable in that case for less than 1,000 kilometers. No.
Okay. One minor
It's
correction.
usually for yeah.
In PPT, it's
Yeah, sure.
not technical. I think in bracket you missed SBS and SRS reverse. So you
Yeah,
can correct
yeah.
it later on. Yeah.
Yeah, thank you. Thank you for reminding. Yeah, I saw it now. Yeah, thank you. So we are also planning in future, coming future, to at least observe this in effect in lab and see whether this is present in our system as well or not. So that's all for today. I tried to cover most of the effect in time. I will share the PPT and the recorded video, and if you have any question, you can ask.
I have one question. Like,
Yeah.
did you try to configure all 88 channels and see the effects of nonlinearity anytime?
I personally,
because
yeah. I mean, first of all, we not me personally, but I think Eli did something like this with large number of channels, like AC channels, basically, the COM channels, basically COM frequencies, and he tried to see something. I remember. I need to check in with him, but I think he tried to see these effects. Yeah.
But with noise channels, are we able to simulate it in a correct way?
Not exactly, but still we have some ideas. Yeah.
Okay.
I mean, of course, we need the real channel, but 88 channel is difficult to find.
Yeah,
so
correct.
on the comms.
Right.
Yeah.
Okay, thank you.
Thank you, Avi. It was wonderful session.
Abhishek, I have a question here.
Yeah, sure.
As beginning of the session,